To find the area or probability of a normal curve, we use the z-score formula, x minus mu over sigma. So let's look at an applied problem. The birth weights in a European country are normally distributed with a mean of 3,570 grams and a standard deviation of 500 grams. What we want to know is, what is the probability that a random birth weight in this country will be less than 2,700 grams? So we're going to go in and find our mean and standard deviation, our mu and sigma. So mu, we know, is 3,570, and we know that sigma is 500. And what we want to know is the probability that the random birth weight selected in this country will be less than 2,700. So x is going to be less than 2,700. Once we got all of that set up, we just plug into our z-score formula and see what we get. So z equals 2,700 minus 3,570 divided by 500. And when we do that, we're going to get negative 1.74. So not too bad. But now we need to find out the probability. So we're going to go to normal CDF in our calculator. And we want it to be less than 2,700. So that means we want everything less than negative 1.74. So we're going to pick an arbitrarily large negative number, negative 9999. And then our upper bound, as high as it can go, is negative 1.74. And then we're going to find the probability from this. So bring up our calculator. And we're going to go to second in vars, normal CDF. And then we're going to do negative 9999, comma, negative 1.74. And then hit enter, and we're going to get this number here. So we're going to get a 0.0409 as our probability that you will find a random birth weight less than 2,700. Now let's go on to the next one. What is the probability that a random birth weight in this country will be greater than 3,600? So again, we know our mu and sigma, they have not changed since the first part. So still 3,570 and 500. But this time we want it to be, our x to be greater than 3,600. So x is going to be greater than 3,600. So find our z-score. So 3,600 minus 3,570 divided by 500. And when we do that, we're going to get a fairly small number. We're going to get 0.06. And now we're going to do normal CDF. And since we want it to be greater than 3,600, it needs to be greater than 0.06. So our lower bound is 0.06 to an arbitrarily large positive number, so just quadruple nines. And then we're going to plug this into our calculator. So bring our calculator up. And we're going to go to second in vars, normal CDF, and 0.06, comma, 9999, close parentheses and enter. And we're going to get 0.4761, so 0.4761. So the probability of a random birth weight being greater than 3,600, 0.4761. Now, what if we want to know what birth weight separates the top 5% of all birth weights? So what x value separates the bottom 95 from the top 5? So again, we know our mu, which is 3,570, and we know our sigma, which is still 500. But we got to find z so we can solve for x in our z-score formula. So we're going to go to inverse norm. And we're going to find again the bottom percent, which is going to be bottom 95. So when we put that into our calculator, I'll bring that up real quick. Where'd it go? There it goes. So second vars, inverse norm of 0.95. So 0.95 is our area. We're going to hit enter. And we're going to get 1.64. So 1.64 to 2 decimal places. And now we're going to plug it in to our z-score formula so we can get our x value. So 1.64z, so 1.64 equals x minus 3570 over 500. So we're going to take the 500 and we're going to multiply it over by the 1.64, and we're going to get 820 equals x minus 3570. And then we're going to add 3570 over to the 820, and we're going to get 4,390 as x. So what birth weight separates the top 5% of all birth weights? 4,390 grams.